we've talked about the Lagrangian, we've talked about the Hamiltonian, and now we talk about the dynamic programming approach. So for a deterministic dynamic programming problem, the solution algorithm starts by finding the best solution for each possible state at the last stage, and the algorithm proceeds backwards using a recursive relation, one stage at a time. For example, this V star t is the value today. V star t plus 1 is the value tomorrow or next year. So what this says is that we want to maximize, if we're in today, we want to maximize our decision. So J refers to the decision that we take. So J means we have various kinds of decisions. For example, we might think of them as different levels of harvest or different levels of effort put into harvest. And Rij, I is the state variable here, and J is our decision variable. So this is exactly what we had before. This is like the price times the harvest minus your cost. V star, on the other hand, implies that you've got an I here, and that anything that you do, the choice you make here, affects the return, but it also affects the future. But what you know about the future is that next year you have made a decision that is also going to be optimal. And you also know that the decision in the past year is optimal. All right, so the star indicates that the decision that you make in any given period of time is going to be optimal. Okay, notice that T here determines a stage, and it need not necessarily be related to time, but in economics it tends to be related to time. So Bellman's functional recurrence equation in discrete time looks like this, all right, where V of t depends on what you're going to do in the future, all right, and in the future you're going to make an optimal decision. We're going to work with this functional form later on in the course. The continuous time problem looks like this, and I'm going to skip over this more quickly, where we have some value function and it's equal to the maximum, the decision you make, u, and it goes from little t, some period in time, we're making this decision at a given point in time, up to big T, the time horizon where the time ends. And we have that the function is a returns function, a function of the state variable, the control variable, and time. And S here is simply an integration variable because we're using T over here. Xt is given. So the starting value is given, and or it's given at any point in time. The terminal condition is given, and x dot s is given by this expression here. Now we're going to drop the time variable for convenience, but we solve this problem and we can rewrite it like this in terms of a delta t. All right. So what we're basically doing here is by introducing delta t, we're trying to convert that situation here into this continuous time problem into an expression that looks very much like the discrete time problem. All right. We evaluate the integrals and assume that delta t is very small and allow delta t to approach 0, and we allow this expansion term to approach 0 as well. So this term gets eliminated. We assume that v is continuously differentiable, and that expression turns out to look like that. And we substitute it into equation 1, and basically we get an expression that looks very much like that. Okay. We cancel the vxt on both sides of equation 2, divide by delta t, and let delta t approach 0, and then we get, upon rearranging things, we get a partial differential equation, which is known as a Hamilton-Jacobi-Bellman equation. All right, or at least it has that form, but you'll notice that it looks very much like what we had before in discrete time. And we can look at that when we have a discount factor in here, we get the Hamiltonian Jacobi-Bellman equation for non-autonomous time-dependent case, which looks like that. All right, for the autonomous system, we get, when we're discounting, the expression looks like this. And we can also look at the ordinary differential equation that results as well. I wouldn't worry too much about some of this, except that we want to relate the dynamic programming and the Hamiltonian, which is done on this slide. The thing that we do want to look at is what's called the augmented Lagrangian function. And that is where we have a situation where we're maximizing something over time, subject to a dynamic constraint, plus a static constraint. So the dynamic constraint tells us how things proceed over time, how the system moves over time as a function of the state variable and the control variable. But in every period of time, there's a further constraint, which looks like this. All right, this g of x u t is equal to 0. So here we have n of these constraints, dynamic constraints, and m static constraints. So that makes the problem somewhat more difficult. We can find the Hamiltonian as usual. The Hamiltonian is given by this objective plus these constraints, these dynamic constraints. All right, where pi now is your shadow price over time, your dynamic shadow price. And we now have an augmented Lagrange function, which includes this Hamiltonian and all of these individual constraints that must hold in any given period of time. All right. So the co-state equation now looks like this. State equation and the maximum principle come like this, and this is a rank condition, and then the problem can be solved in much the same way. Now with inequality constraints, the problem looks a little bit different, and I'll let you look at that. But at this point, I tend to ignore this kind of thing, and what I tend to do is I fall back on mathematical programming, as this is the best way to look at that. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.